Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says to draw the Lewis structure for hydrogen peroxide. It also asks what is the weakest bond in hydrogen peroxide, and hydrogen peroxide is sold commercially as an aqueous solution in brown bottles to protect it from light. Calculate the longest wavelength of light that it has sufficient energy to break the weakest bond in hydrogen peroxide. Okay, so first let's draw the Lewis structure of hydrogen peroxide. And to do so, we're first going to calculate the total number of valence electrons in the molecule. Okay, so hydrogen has one valence electron, and there are 2 hydrogen atoms, so we multiply this by 2. And in the case of oxygen, there are 6 valence electrons, and we also have 2 oxygen atoms, so we would just multiply this by 2 as well. Okay, so 12 plus 2 is 14. So we have 14 valence electrons. So first we're just going to draw our oxygens with a single bond. And then each of those will have a single bond to hydrogen. And from here, we just fill out all of the lone pairs on the oxygens. And if we count out how many I've drawn so far, we have 2 electrons in each bond. So that is 6 plus 8, so that is 14. So this is our final Lewis structure for hydrogen peroxide. Okay, so the second part of the question says, what is the weakest bond in hydrogen peroxide? Okay, so hydrogen is it is the smallest element on the periodic table. So I'm just going to write that oxygen atoms are much larger than hydrogen atoms. So therefore, the intermolecular distance in a bond containing hydrogen and oxide is much smaller than the bond between the 2 oxygen atoms. So the longer bond, which is the 2 oxygen atoms, is the weakest. So the smaller bond you have, the stronger bond it is. So since the 2 oxygen atoms have a longer bond, this will be the weakest bond in hydrogen peroxide. So now let's do part C of this question. We need to calculate the longest wavelength of light that has sufficient energy to break the weakest bond in hydrogen peroxide. So to do this question, let's first recall this energy equation, where energy is equal to Planck's constant times the speed of light divided by your wavelength. So we can rearrange this equation and solve for wavelength. So if we solved for wavelength, it would be hc divided by E. So now let's just plug in all of the values. So Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And the speed of light is 3 times 10 to the 8 meters per second. Okay, so now for E, we need to find the bond enthalpy of the two oxygen atoms. So I'm just going to look it up on Google. So the bond enthalpy between two oxygen atoms is found here, so it is 146 kilojoules per mole. And before I before I do any calculations, I want to make sure that all my units should cancel out. So instead of kilojoules per mole, I'm going to convert this to joules just by multiplying it by 1,000. So now if we multiply this through, we end up getting around 1.36 times 10 to the negative 34. And the units, if we see here, is meters times moles. So now I have an answer that is in meters, but because it is in moles, I want to get rid of that and try to figure out the energy to break the weakest bond in hydrogen peroxide. So I'm going to multiply by Avogadro's number to get the units that I need. So Avogadro's number is 6.023 times 10 to the 23. So let me just write mole in. And the units for Avogadro's number, I'm just going to say atoms per mole. And now our units for moles will cancel out. And then we have our answer in meters, which is 8.2 times 10 to the negative 7 meters. And if we converted this to nanometers, then it would be the same as 820 nanometers. Okay, so let's see what the junior tutor said. Hydrogen has 1 valence electron, while oxygen has 6. Hydrogen follows a duet, while oxygen follows an octet. Okay, so they have a more accurate Lewis structure, but it is pretty much the same. And B, oxygen has a bigger radius than hydrogen. We have either hydrogen or hydrogen-oxygen or oxygen-oxygen bonds to choose from, and from the nature of the atom's radii, the hydrogen-oxygen bond will be shorter and thus stronger. The weakest bond should be the oxygen-oxygen bond. Okay, so for part C, they wrote the bond enthalpy of the oxygen-oxygen bond and got 146, and they showed their energy equation. Okay, so they plugged it in to the equation, multiplied that value by Planck's Avogadro's number, and also got 820 nanometers. So this solution is correct.